Okay, so we got the TDS equation here. Let's see what it reduces to under certain specific material conditions. So first of all, let's look and see what happens when we have a solid or a supercooled liquid. So solid or super or some kind of a liquid. Now the characteristic of a solid or a liquid is incompressible, no change in volume or specific volume, no change in volume or specific volume over the process. So incompressible. So any process involving a solid or a liquid, we can assume to be an incompressible process. So in that case, so let me write the first version of the TDS equation. So we have TDS is equal to du plus PdV. Now, if it's incompressible, there's no volume change. So this term is equal to 0 because we're incompressible. So that goes away. And so I'm left with TDS is equal to du. Now, du for a solid or a liquid is equal to CV dt. So this is CV dt, where specific heat can be either constant or variable. And so the final result here is ds is equal, this is actually mass times specific volume. So why don't I be a little bit more careful here? Mass times specific volume times CV dt. So du is equal to the mass times CV dt. So I get ds is equal to m CV dt over temperature. So I take the temperature on the left-hand side, put it on the right. And the last version I'm going to write of this for a solid or liquid is I'm going to divide both sides by the mass of the system. So I'm going to get the change in specific entropy, the differential change. D little s is equal to CV dt over temperature. So this is the change. Differential change in entropy is equal to the specific heat times the differential change in temperature divided by the temperature of the system. Now, if I want to get the overall change in entropy, so we have a liquid or a solid. So liquid or solid, whatever. And we start off with a temperature T1, and I go to a temperature T2, and I want to know what the change in entropy is. All I need to do is integrate that equation. So I've got a temperature T1, I have an S, specific entropy at state 1, I have a specific entropy at state 2. So to get the change in entropy, delta S from 1 to 2, which is S2 minus S1, this is specific entropy, is equal to the interval of CV dt over temperature, from temperature 1 to temperature 2. Okay? So let me write this up here. For a solid or a liquid, delta S, the change in specific entropy over a process, is equal to the integral of CV dt over temperature from T1 to T2. So that's a general expression, or variable specific heat. And of course, if we assume constant specific heat, the CV gets pulled out of the integral, and I get CV times, and then I can evaluate the integral. The antiderivative of 1 over t is natural log of t. So I get CV ln T2 over T1, and this is for constant CP CV, okay? So for liquid and solids, depending on whether you're using variable specific heat or constant specific heat, the change in entropy is given by either one of these expressions for a liquid or solid. I put a box around this. Liquid or solid, expressions for calculating the change in specific entropy of the liquid or solid, okay? So that's for a liquid or solid. Of course, if you're inside the dome, so in this case here, I guess I should, maybe it wouldn't hurt to put up the saturation dome and indicate what region we're talking about here. So here's specific entropy, here's temperature, here's the dome. So I'm interested in calculating delta S out in this region here. So this is for liquids. Okay, that's out here, okay? So that's how we calculate delta S to the left of the surface of the saturation dome, okay? What about if we want to calculate change in entropy for an ideal gas? So how about IGB? IGB. What about ideal gas behavior? We'll talk about constant versus variable specific heat in a minute, but let's start with the TDS equations. So TDS is equal to du plus PdV, and then I have dH plus VdP. By the way, maybe at this point, it might be good to divide both left and right-hand side by the mass of the system. So if we divide by mass, everything becomes lowercase. So I can also write this in terms of specific entropy, internal energy, and volume. So Td lowercase s is equal to lowercase u du plus pressure times d specific volume, or dH lowercase a minus, dH minus VdP, not plus, minus VdP. Did I get the, yeah, I got the right one over there. So, and that's specific volume dP, okay? So that's on a per unit mass basis. Well, let's play around with the first equation here. So Td little s is equal to du plus PdV, okay? Now, du is equal again to Cv dt, okay? That's from the property relationship for change in internal energy. Now, pressure. From the ideal gas law, pressure is equal to what? mRT over V. mRT over V. And of course, I can write this as RT over specific volume. Divide volume by mass, and you get specific volume. So this guy is actually equal to Cv dt plus R over T divided by specific volume dV. Okay, that's what TDS is equal to. Now let's divide both sides of the equation by the temperature. And I get ds, change in specific entropy, is equal to Cv dt over temperature, plus the temperatures will cancel out, and I'll get R over specific volume, d volume. Ideal gas comes in with the substitution for pressure in the TdS equation, okay? Now to get delta S over the process, we integrate this equation. So we get delta S from 1 to 2 is equal to the integral of CV dt over T from temperature T1 to T2 plus the R will come out of the integral, R, and then you'll have the integral dV over V from V1 to V2. Now again, the antiderivative of specific 1 over specific volume is a natural log. So this guy here, this term becomes R ln V2 over V1. Okay, so the final equation we have here, delta S. Delta S 1 to 2 equals, let me write the variable specific heat. I'm going to keep the CV inside of the integral. So I got the integral CV over T dt from T1 to T2 plus R ln V2 over V1. Okay, that's the first equation we get for the change in specific entropy for an ideal gas. That's the equation involving CV. There's a CV in this equation, that integral right there. There's also another version of this. Let's deal with the DH equation, one that has H in it. Let's do the same process here, but now we'll do it for the second equation in the TdS equation. The second equality, the lower one. So I have TdS is equal to dH minus VdP. Okay, that's the second equation right there. dH is equal to Cp dt from the property relationship. Cp dt, property relationship, dH is equal to Cp dt. And then specific volume from the ideal gas law. Let's see, specific volume is volume divided by mass. So that's RT over P. RT over pressure. So I get Cp dt minus RT over pressure d pressure. Okay? Now I'm going to divide this entire equation by temperature, and I get ds is equal to Cp over temperature, d temperature, minus the temperatures cancel out in the second term, R over P, I'll make my R a little smaller, R over P dP. Okay, so we use the ideal gas law to get rid of the specific volume in the second term. And we got a pressure in there instead. Now let's integrate this to get the change in specific entropy over a process for an ideal gas. Delta S from 1 to 2 is equal to the integral Cp over T dt from T1 to T2 minus. Now we're going to have an integral of R over P dP. Integral R over P dP from P1 to P2. Take the R out of the integral, and the antiderivative of 1 over pressure is the natural log of pressure. So this term here becomes R ln P2 over P1. Okay? So the final version, second version of the expression for delta S for an ideal gas is integral Cp over T dt from T1 to T2 minus R ln P2 over P1. Okay, so that's the expression for change in specific entropy for an ideal gas over some process 1 to 2. Now, for constant specific heats, CB and CP pull out of the equation. So constant, note, constant CP and CV, we get the following. Delta S 1 to 2 is equal to, and I have two expressions. I can pull the CV out of the integral, the first integral, and I get the integral of 1 over temperature d temperature. The antiderivative of 1 over temperature is natural log. And I get CV ln T2 over T1 plus R ln V2 over V1. Okay, constant specific heat, that's what the first equation reduces to. The second equation involving enthalpy, or CP if you like, I can pull that out of the integral as well. And the only difference is I'll have CP ln T2 over T1, and then I'll have a minus R ln P2 over P1. Okay, so for constant specific heat, you can pull the CP and the CV out of the first integral on both those expressions, and you can evaluate the change in entropy directly. You can evaluate the change in entropy delta S directly. So let's put a little box around this. So this is for constant specific heat. I know most of you like to do problems assuming constant specific heat. It makes calculations so much more easy. Now, what about variable specific heat? This is the variable specific heat expressions for delta S. Note that the CP and CV, which are functions of temperature, are still buried in the integral. I haven't assumed that they're constant, and therefore I haven't extracted them from the integral to get these easy expressions here. So how do we evaluate delta S for variable specific heat? Well, what they did was, or what is done, is that this second equation, this term right here, is tabulated. It's actually equal to a difference in two quantities. The integral represents a difference in two areas. The whole definition of the integral is one area minus another area. Or if you like, some antiderivative evaluated at the forward position versus at the backwards position. So it's a difference in two quantities which is used to evaluate the integral. Okay? So what they did was they re-expressed this integral as the difference between two quantities which are functions of temperature. So this guy here is equal to what's called S naught evaluated at T2 minus S naught evaluated at T1. So our new expression for variable specific heat, for variable CP/CV, our new expression is delta S from 1 to 2 is equal to S naught T2 minus S naught T1 minus are ln P2 over P1. Now, where are these S naughts found? S naught is a function of temperature in tables. Let's find them. Let's find them. We'll be doing an example here pretty soon showing you how this is done. Let's see here. So let's go to IGB air tables and see what we can find. IGB air tables. Refrigerant. Oh, we'll be dealing with that later. Here we go. Actually, I think my notation's a little bit different here. So we have, as a function of temperature, enthalpy, internal energy, and S naught. I guess I'm using an uppercase S naught there. I'll go change the notation in just a second. So S naught is a function of temperature, and S naught, or the difference in S naughts evaluated at your upper and lower temperature, allow you to calculate the integral Cp over T dt. So these are available in ideal gas tables, whether it's for air or for nitrogen, oxygen, water vapor, CO, CO2. You see these S naughts? The S naughts are used to evaluate. They're used to evaluate the integral Cp over T dt. So I guess I've got to be a little bit careful here. In the notes, I'm using S superscript naught. So I guess I have to make sure the notation, S superscript naught, okay? So if you're doing a variable specific heat problem, to account for variable specific heats, you want to use this S naught formulation for calculating delta S, where the S naughts are located in tables. Okay, this is a lot of stuff going on. You've seen a lot of property relationships. You've now got this TDS stuff. You have the DU, the DH. There's a lot of stuff. I'm sure some of you are thinking, how in the hell am I going to remember all this stuff? It's just overwhelming. It perhaps is. That is why I have made a little table for you in the notes. Let's see if we can find it. So let's go to, excuse me. Let's go to the notes here, and let's go to chapter 6, which is the one on entropy. I always forget whether it's 6 or 5. Let's see here. Chapter 6. Let's go to the various property, the TDS equations. TDS equations. Let's see if we can find it. It's here somewhere. Might be at the end of the chapter. Let's see here. I don't know where it is. I guess I have to look for it. There we go. Right at the end of, or prior to, yes, we have review of property relationships. So section 6.5, which is on page 125, just prior to it, you will find a big full-page table that reviews and gives you the various property relationships depending on the substance. So we have, and also the basis. So we have differential process, differential per unit mass, overall process per unit mass. So that's what these are about. And then I have internal energy and enthalpy relationships valid everywhere. And that means everywhere. Ideal gas, solid, superheated vapor, mixture, whatever. And then I have IGB property relationships. Valid, not valid inside the saturation dome. And then I have constant specific heat and IGB equations here. Okay, so notice you have this S naught stuff in the variable specific heat IGB formulations. You see it right here. And then you've got CV and CP, ln T final over T initial, or T1 over T2 if you like, for the constant specific heats. Okay, so if you're dealing with ideal gas and you don't know what to do, or you're dealing with some sort of a general situation, you can go to this table and you can attempt to figure out how to calculate delta S. And again, I would also recall that we went over calculating delta S for incompressibles. So that section, if you want to look at it, is section 6.3.2. So here's our ds is equal to Cp dt over T. Little clarification here. I wrote Cp here, but on the board, I wrote CV. CV instead of Cp. Guess what? It doesn't make a difference whether you, for an incompressible, whether you use Cp or Cv. Why? Because the only difference in specific heat for a constant versus a pressure versus a constant volume process is the presence of boundary work. And guess what? For an incompressible, there's no boundary work. It doesn't matter whether the pressure goes up and down, doesn't matter whether the pressure goes up and down for a solid or a liquid. The volume doesn't change because there's no boundary work. It's incompressible. And so Cp and Cv are numerically identical for solid and liquid. So in the textbook, delta S for a solid or liquid is Cp over T dt. And of course, you integrate to get delta S. And I wrote it Cv here. It doesn't matter which one you do because there's no boundary work for a solid or a liquid. So Cp and Cv are numerically identical. All right, ladies and gentlemen, I think that's enough for today. So you've been introduced to the property relationships, the TDS property relationships, as well as how to evaluate changes in entropy for an ideal gas and incompressibles using those relationships. Next class, we will go over some examples. Take care.